Good day, everyone. Okay, so uh, this will be the part 3 of our series in stresses and beams, shear stress. Okay, so uh, in the previous two um, videos, we have discussed how we use this formula. Okay, how we compute uh, any random stress on your stress diagram. Okay, so technically speaking, in a rectangular section, it is parabolic. Okay, it is parabolic in shape. So I would like to clarify that this stress distribution is only applicable. Okay, it is applicable. Okay, its shape would be parabolic if the shape of its cross-sectional area is rectangular. Okay, so what about the other shapes? Okay, so I would like some rectifications, okay, to this. So technically speaking, for example, in a circle, okay, so there is always a change, okay, as the point of stress, or as the stress we are looking upon is increasing. So the B is always changing, okay? Starting from 0 until if it reach somewhere at the middle, okay, at the diameter, it will be at stress max. And but also its B will be at its maximum. So therefore, since your B is increasing up to the neutral axis, so this curve, okay, will be almost the same shape, but it is quite flat. Okay, so it would be like this. Okay, it's not parabolic. Okay, it's not parabolic anymore, but it's more likely the square root of, okay, square root of it would be like this. It would be more closer to a square root form. Okay, slightly flattened since the B is increasing from top to bottom. Okay, so here, okay, for the I-beam, I would like to clarify, since the B here at the web is large, so there is a possibility that at that instant that it will be a parabolic curve, these portions at the side would decrease so much because the B here is larger than at the flange. So what will happen, it would be similar to parabolic, but this portion will be very small. Okay, it would be like this, and then it would suddenly increase when it is transferred to when we go to the flange. Okay, the stress diagram will be like this. It will be curvilinear at this point. Okay, flattened curvilinear, but somehow because the B suddenly decreases, okay, I mean decrease some here at the flange, so the shape of your stress diagram will be like this. Okay? So look like a fish, okay? It will be like this, okay? Okay. So I explained to this, I explained to you this so that you will understand better how the stress distribution um, will be according to the shape of your cross-sectional area. And how you can deduce the shape of your your shear stress distribution, okay? Specifically shear stress distribution, um, okay, which is parabolic in shape when it is rectangular beam. So what will be its approximate shape when it has a different shape? It might be circular, it might be an I-beam form, triangular or trapezoidal. So here, for triangular, since its B is increasing from the top, it will be 0, but somehow, okay, you might say it is undefined, but somehow it's still 0 at here at the top, but somehow it will be very skewed. Okay, it would be more similar to a nose. Okay, so since the B is constantly increasing from the top until it will reach its biggest B, okay, B max here. So therefore, the shape of your stress diagram will be similar, very similar to a nose. Okay, it would look like a nose, a pointed nose. Okay, look. So your stress max is located h over 3 at the from the bottom. Okay, so I hope you understand. Also for trapezoidal. Okay, so if the shape of the stress distribution, okay, shear stress distribution of your triangle looks like a nose. So the shape of your trapezoidal cross section, since it already had a smaller value at the top, letter B, so expect that, okay, if you compare it, okay, using your imagination from a rectangular beam, so more likely it would be bigger at the beginning. Okay, the stress distribution will be bigger at the beginning since it has a smaller B, but somehow, okay, it would be like this. It would be also looking like a nose. Okay, it is slightly skewed downward, just like your your rectangular shape. Okay, so this is not parabolic anymore. Okay, but somehow it is quite skewed. Okay, I mean, it is not asymmetric parabolic anymore. It is skewed downward. Okay, since your the location of your, let us say, y bar, or the location of your centroid uh, parallel to y axis is nearer from the bottom than at the top. So it's the shape of its shear distribution is more likely skewed downward. Okay, so these are the different shapes, okay, of stress distribution depending on the shapes of your cross-sectional area. Okay, so the only thing that is weird here is this the stress distribution of your um, eye section. It's because it looks like a fish. Okay, so I hope understood. Okay, so I will rectify my drawing. Okay, sorry. Okay, so starting from here, okay, so in the next videos, we will be solving some example problems. Okay, so that you will understand better our lessons. Okay, thank you.